Welcome to Sleep to Science. Tonight, we're exploring that faint band of colors that appears after thunderstorms. You've seen it countless times arcing across rainy skies. But have you ever wondered what's really happening up there? Every rainbow tells a story about light that most people never hear. They reveal secrets about how your eyes work, how your brain organizes the chaos of nature into neat categories, how millions of water droplets become tiny optical laboratories floating in the sky. We'll discover why Newton's famous seven-color system has almost nothing to do with what's actually happening in the atmosphere. You'll see how each microscopic water sphere performs precision optics that would impress any engineer. And we'll explore why you can chase a rainbow your entire life without ever getting one step closer. So settle in. Before we begin, leave a quick note in the comments, where you're listening from, or one thought you're carrying tonight. I read them, and they genuinely help shape future journeys. If you'd like more nights like this, subscribe. Only if you enjoy these late-night journeys. Now let's begin. Children everywhere have chanted the same magical spell for 3 centuries. Red, orange, yellow, green, blue, indigo, violet. Teachers present it as scientific gospel. Artists treat it as nature's blueprint. But here's the secret nobody mentions. This famous rainbow recipe came from one brilliant man's personal obsession. Picture Isaac Newton in 1666. He sits in his darkened room at Trinity College. Sunlight streams through a triangular piece of glass. Something extraordinary happens. White light explodes into a continuous river of color. Deep red flows into brilliant violet, an endless spectrum without boundaries. Newton faces a cosmic puzzle. How do you organize infinity? At first, he sees exactly what nature produces. 5 flowing regions of color. Red melts into yellow. Yellow dissolves into green. Green flows into blue. Blue deepens into violet. No sharp edges anywhere, just pure liquid light doing what light does naturally. But by 1704, Newton publishes his revolutionary work Optics. He's mysteriously expanded his list to 7 colors. Orange and indigo have appeared from nowhere. Why 7? Newton believes the cosmos operates on divine mathematical harmony. The same mystical proportions that create musical scales should govern light's colors. He wants his rainbow to sing like a celestial harp. Each color should match a musical tone in perfect cosmic symphony. This isn't scientific discovery. It's artistic wishful thinking. Newton grabs a celestial marker. He draws arbitrary lines across nature's flowing masterpiece. He decides where red ends and orange begins, where blue stops and indigo starts. Those boundaries exist only in his mind. Yet his 7-part framework becomes so powerful it rewires human color perception across the entire planet. For over 300 years, we've been seeing rainbows through Newton's eyes, not our own. What if everything you learned about rainbow colors was backwards? Every rainbow contains roughly 1.5 million distinct colors flowing in an unbroken river. These wavelengths stretch from red at 700 nanometers down to violet at 380 nanometers. These aren't separate colored bands, not rainbow cake layers stacked neatly. They're one continuous spectrum where each wavelength melts into the next, like an infinite watercolor painting that never stops blending. Your eyes experience this flowing light show through 3 types of cone cells. Red sensitive, green sensitive, blue sensitive. Here's where the magic trick happens. Your brain takes millions of wavelength combinations and performs constant translation work. It converts nature's infinite complexity into familiar color categories Newton taught the world to expect. When yellow light hits your retina, you're not seeing a distinct yellow stripe. You're experiencing your brain's interpretation of wavelengths around 570 nanometers, all filtered through 3 centuries of cultural programming. The seamless nature becomes obvious when you try something simple. Try to pinpoint exactly where yellow ends and green begins in an actual rainbow. The boundary vanishes under inspection. Colors flow like water. Each wavelength shares characteristics with its neighbors in endless progression. What we confidently call orange actually represents thousands of distinct wavelengths, each one vibrating at its own unique frequency, each one carrying its own electromagnetic signature. This continuous light river extends far beyond human vision. Below red lie infrared wavelengths that pit vipers use to hunt warm prey. Above violet stretch ultraviolet wavelengths that guide bees to flower nectar we can't see. The narrow slice we call the rainbow represents just one tiny window. Here's the remarkable part. Every water droplet in a rainbow cloud splits sunlight into this complete continuous spectrum simultaneously. Millions of microscopic spheres act as individual light-splitting factories. Each produces the full range of visible wavelengths with precision that would make human engineers weep. The rainbow you see represents collective optical work. Countless droplets contribute their own seamless light rivers. Together they create that magnificent band of flowing color spanning the sky, a natural phenomenon far more sophisticated than Newton's 7-part filing system could ever capture. Somewhere above the clouds, millions of microscopic optical laboratories prepare for the world's most spectacular light show. Each water droplet suspended in the atmosphere operates as a precision instrument. These tiny lenses would cost thousands of dollars to manufacture in any human laboratory. Nature mass produces them by the billions, then deploys them across miles of sky in perfect formation. When sunlight encounters a single raindrop, magic happens in 3 stages. First, the light beam slows down as it enters the water sphere. This deceleration bends the light ray toward the droplet's center through refraction. Different colors bend by different amounts because they travel at slightly different speeds through water. Red light barely changes direction. Violet light bends much more dramatically. Inside the droplet, separated colors bounce off the curved back wall like light reflecting in a spherical mirror. This internal reflection sends the rainbow spectrum racing back toward the front of the droplet. But here's where the physics gets truly elegant. As the light exits the water sphere, it bends again. This double bending process spreads the colors even further apart. Each droplet acts like a tiny rainbow factory with perfect quality control. Red light always exits at exactly 42 degrees. Violet light emerges at 40 degrees. The other colors arrange themselves between these boundaries in perfect spectral order. Every single droplet produces exactly the same result with clockwork precision. No variation, no defects. Just flawless optical performance repeated millions of times across the sky. The rainbow you see represents the coordinated light show from countless droplets positioned at exactly the right distance and angle from your eyes. Droplets closer or farther away contribute nothing to your rainbow. Only those spheres located precisely 42 degrees from your line of sight participate in the display. It's as if nature organizes millions of tiny spotlights into perfect formation. Each one contributes its own sliver of spectrum. Together they create that magnificent arc of continuous color stretching across the heavens. Most people never realize they're witnessing the universe's largest coordinated optical performance, featuring millions of individual performers, each one a microscopic master of precision optics. Every culture tells stories about treasures hidden at rainbow ends, leprechaun gold waiting to be discovered, magical kingdoms accessible to brave explorers. These legends persist because nobody has ever actually arrived at a rainbow's endpoint, but the reason isn't lack of effort or bad luck. It's fundamental physics. Rainbows don't exist in any fixed location you could visit with hiking boots. They're personal optical experiences created by precise relationships between three elements: the sun behind you, millions of water droplets in front of you, your eyes occupying exactly the right position to intercept the light show. Move your position even slightly, and you're seeing a completely different rainbow, one created by entirely different droplets. Here's what actually happens when you chase a rainbow. As you run toward where the rainbow appears to touch the ground, the droplets creating that rainbow image become too close. They can no longer maintain the correct 42-degree angle with your eyes. Those particular droplets can no longer contribute to your rainbow. Instead, droplets farther away take over the display. The rainbow appears to move away from you at exactly the speed you're running toward it. From your perspective, the rainbow maintains the same apparent distance no matter how fast you travel. It's like chasing your own shadow. The phenomenon moves with you because you're an essential component of its creation. Other people nearby see their own unique rainbows. Different collections of droplets create each person's display. Everyone experiences their own personal light show. No two observers ever see exactly the same rainbow. Aircraft pilots sometimes witness the ultimate rainbow experience that ground observers can never share. Flying at the right altitude with appropriate weather conditions, they occasionally spot complete circular rainbows. These perfect rings surround the aircraft's shadow on cloud layers below. From the ground, we see only the top half because Earth blocks our view of the bottom arc. But the full circle exists, waiting for anyone willing to climb high enough to see the complete picture. Every rainbow represents a private screening of nature's light show, performed exclusively for an audience of one. Rainbows appear deceptively simple. Sunshine plus rain should equal instant rainbow magic, right? Mother Nature operates a much more exclusive club. She demands precise atmospheric conditions before approving any rainbow performances. Most weather situations fail to meet her strict requirements. The average person witnesses maybe 5 to 10 rainbows per year if they're paying attention. The sun must occupy exactly the right position in the sky. Too high, and no rainbow appears at all. The solar angle cannot exceed 42 degrees above the horizon. During summer months at mid-latitudes, this limits rainbow opportunities to early morning and late afternoon hours. Winter provides longer daily windows because the sun stays lower, but winter also delivers fewer rainstorms suitable for rainbow production. Rain droplets need precise specifications for optimal rainbow generation. Too small, and the droplets don't bend light effectively. Too large, and they fall too quickly to maintain stable aerial positions. The ideal rainbow storm produces medium-sized droplets that hover at roughly the same altitude. The geometry requirements eliminate most weather scenarios. You need sunshine behind you and rain in front of you simultaneously. This arrangement occurs mainly when storm systems move through rapidly. Passing weather fronts create the classic setup. A blue sky opens behind departing clouds while rain continues ahead. These transition periods usually last just 10 to 20 minutes. Miss the window, and you wait for the next atmospheric lottery drawing. Wind conditions matter enormously. Gentle breezes help maintain steady droplet positions. Strong winds scatter the droplets too much for coherent rainbow formation. Turbulent air creates constantly shifting droplet patterns that prevent stable color bands. Light pollution in urban areas reduces rainbow visibility even when atmospheric conditions cooperate perfectly. City illumination washes out faint rainbow colors against bright sky backgrounds. Rural observers enjoy distinct advantages for rainbow spotting. Modern life keeps most people indoors during prime rainbow hours. Storm conditions typically send everyone inside seeking shelter. The irony is profound. Rainbow weather encourages humans to avoid the outdoors exactly when nature prepares her most spectacular optical displays. Sunlight looks perfectly white streaming through your window. Clean, pure, simple. That's exactly what humans believed for thousands of years. Ancient Greeks thought sunlight represented the purest form of light possible. Medieval scholars assumed white light contained no hidden components whatsoever. Even brilliant minds like Galileo never suspected what was actually flowing down from our nearest star. The truth would have horrified those early thinkers. What appears as clean white light actually contains a secret rainbow cocktail. Millions of different colors blend so thoroughly that your eyes can't detect the individual ingredients. We're not seeing pure white light at all. We're witnessing the combined effect of countless colored wavelengths hitting our eyes simultaneously. Here's how the cosmic deception works. Sunlight contains every possible color wavelength from deep red around 700 nanometers down to violet near 380 nanometers. These wavelengths don't travel separately. They journey together as one unified beam across 93 million miles of space. Red light mingles with orange. Yellow blends with green. Blue mixes with violet. The result appears white because your eyes average all these colors together into a single neutral impression. Think of white light as nature's ultimate smoothie. Imagine blending every fruit in the grocery store together. The individual flavors disappear into one combined taste. Your tongue can't distinguish the original ingredients. Similarly, your eyes can't separate the individual color components hidden within white sunlight. But those hidden colors remain there, waiting. Every wavelength maintains its unique frequency and energy signature, even while traveling disguised as white light. Red wavelengths still vibrate 430 trillion times per second. Violet wavelengths still oscillate at 750 trillion cycles per second. They simply travel together in perfect formation like synchronized dancers performing an invisible cosmic ballet. Scientists call this range of hidden colors the visible spectrum. Stretching from 380 to 700 nanometers, it represents just a tiny slice of the electromagnetic rainbow. This rainbow flows continuously from radio waves to gamma rays. We see only this narrow window because our eyes evolved to detect the wavelengths that penetrate Earth's atmosphere most effectively. Cambridge University, 1666. Isaac Newton sits alone in his darkened study during plague lockdown. Outside, London suffers through the Great Fire and bubonic death. Inside, Newton prepares to conduct an experiment that will change humanity's understanding of light forever. He has no idea he's about to perform cosmic surgery on sunlight itself. Newton arranges a simple glass prism on his desk, just a triangular piece of optical glass borrowed from the university collection. Nothing fancy, no sophisticated equipment. He drills a small hole in his window shutter. One thin beam of sunlight enters his darkened room. Then he positions the glass triangle directly in the beam's path. What happens next defies everything scholars believed about light. The white sunbeam hits the glass triangle and explodes. A magnificent rainbow spreads across Newton's wall like spilled cosmic paint. Red, orange, yellow, green, blue, violet. Colors flow in perfect order from one end of the spectrum to the other. Newton stares at nature's most beautiful magic trick, performed with nothing more than sunlight and glass. But Newton suspects he's witnessing an illusion. Perhaps the glass prism adds colors to pure white light rather than revealing hidden colors already present. Medieval scholars taught that prisms created rainbow colors by corrupting otherwise pure sunlight. Newton decides to test this assumption with brilliant experimental logic. He places a second prism in the path of the rainbow colors emerging from the first triangle. If prisms add colors to white light, the second glass should create even more spectacular rainbow effects. Instead, something remarkable happens. The second prism recombines all the separated colors back into pure white light. The rainbow disappears. Clean white light emerges from the second triangle exactly like the original sunbeam. This proves beyond doubt that white sunlight naturally contains all rainbow colors mixed together. Prisms don't add colors to light. They simply unmix the hidden rainbow cocktail that was there all along. Newton has discovered that every beam of sunlight carries its own secret rainbow soul. Glass triangles merely perform the cosmic equivalent of unscrambling an egg. Every color wavelength behaves like a cosmic speed demon with its own unique personality when traveling through glass. Red light charges through optical materials like an impatient race car driver. Blue light crawls through the same glass like a cautious Sunday tourist. This difference in attitude creates the rainbow separation that makes prism magic possible. The physics behind this wavelength behavior centers on something called the refractive index. When light transitions from air into glass, it must slow down significantly. Air barely affects light speed, but glass forces light to reduce velocity by roughly 33%. This dramatic slowdown bends the light beam toward the vertical direction through refraction. Here's where wavelength personality differences become crucial. Red light with its lazy 700 nanometer wavelength barely slows down when entering glass. It maintains most of its original speed and changes direction only slightly. Red light acts like a heavy truck that's difficult to steer off course. The longer wavelength provides momentum that resists dramatic direction changes. Violet light with its energetic 380 nanometer wavelength behaves completely differently. Short wavelengths interact much more intensively with glass molecules. Violet light slows down significantly more than red light when entering the optical material. This dramatic velocity change bends violet rays much more sharply toward the vertical. Violet light acts like a lightweight sports car that responds instantly to steering adjustments. Orange, yellow, green, and blue wavelengths arrange themselves between these extremes. Each wavelength bends by a slightly different amount according to its unique refractive properties. Orange bends a little more than red. Yellow bends more than orange. Green bends more than yellow. The result creates a gradual rainbow spread where each color occupies its own specific angular position. Scientists measure these differences precisely. Red light bends approximately 1.514 degrees when entering crown glass. Violet light bends 1.521 degrees under identical conditions. That tiny, about 7/1000ths of a degree difference creates the entire rainbow separation you see emerging from prisms. Such a small angular difference, such spectacular visual results. Humans excel at organizing chaos into neat categories. We divide flowing rivers into named sections. We split continuous mountain ranges into individual peaks. We separate seamless color gradients into distinct rainbow stripes. This categorical thinking represents one of our species' greatest strengths and most dangerous delusions simultaneously. The rainbow spectrum flows continuously without any natural boundaries whatsoever. Color wavelengths transition gradually from red through violet like a cosmic watercolor painting that never stops blending. Red melts imperceptibly into orange. Orange dissolves seamlessly into yellow. Green flows endlessly into blue. Nature refuses to draw lines anywhere across this flowing masterpiece. But human brains demand organization. We can't process infinite complexity easily. So we impose artificial boundaries on continuous phenomena to make them mentally manageable. We divide the flowing spectrum into 7 convenient categories because 7 feels psychologically comfortable. Not too few, not too many, just right for memorization and cultural transmission. Different cultures slice the spectrum pie, differently according to their linguistic traditions. English speakers learned 7 rainbow colors because Newton's classification became standard. Russian speakers traditionally recognize 8 rainbow colors because their language contains 2 distinct words for blue. Light blue is goluboy. Dark blue is sini. Russian children memorize both blue categories in their rainbow songs. Japanese culture historically recognized 6 rainbow colors because traditional Japanese treats green and blue as variations of the same basic color family. The word O encompasses what English speakers divide into separate green and blue categories. Japanese rainbow traditions reflect this linguistic difference by omitting either green or blue from their standard color lists. Some indigenous cultures recognize only 3 or 4 rainbow categories. The Himba people of Namibia divide the visible spectrum into fewer color groups that don't match European traditions at all. Their rainbow contains categories that combine what Europeans separate, plus separate categories for colors Europeans group together. Their eyes see the same wavelengths, but their brains organize those wavelengths according to completely different cultural frameworks. The number 7 holds no special physical significance for light wavelengths. Nature doesn't organize electromagnetic radiation into 7 neat piles. The division exists purely as a human convenience for teaching children and organizing artistic traditions. We could just as easily memorize 5 rainbow colors, or 12, or 50. The wavelengths wouldn't change, only our cultural filing system would adjust. Every rainstorm transforms the entire atmosphere into Newton's prism laboratory multiplied by millions. What Newton accomplished with one glass triangle in his darkened study, nature performs simultaneously with countless water droplets scattered across miles of sky. Each microscopic sphere recreates the identical physics that Newton discovered. but scaled up to cosmic proportions that would leave the great scientists speechless. Consider the sheer magnitude of this natural spectacle. A typical rainbow cloud contains roughly 100 million water droplets per cubic meter of atmosphere. Each droplet operates as an individual prism laboratory complete with light entry, internal reflection, wavelength separation, and rainbow exit. Multiply that by cubic kilometers of rain cloud. The mathematical result represents the largest coordinated scientific experiment in the observable universe. Every droplet performs Newton's complete prism sequence in perfect miniature. Sunlight enters the water sphere through the front surface. The light beam slows down and bends according to each wavelength's unique refractive properties. Red wavelengths bend least. Violet wavelengths bend most. The separated colors spread apart inside the droplet, just like rainbow colors spreading inside Newton's glass triangle. But water droplets add extra physics that glass prisms can't duplicate. Inside each spherical laboratory, the separated wavelengths bounce off the curved back wall through internal reflection. This mirror effect sends the rainbow spectrum racing back toward the front of the droplet. As the reflected light exits the water sphere, it bends again according to each wavelength's refractive personality. This double bending process creates much more dramatic color separation than single pass prism effects. The geometry becomes absolutely perfect for rainbow production. Red light exits each droplet at precisely 42.3 degrees from the droplet's center. Orange emerges at 42.2 degrees. Yellow appears at 42.0 degrees. Each wavelength finds its own specific exit angle with clockwork precision. No droplet variation. No manufacturing defects. Just flawless optical performance repeated billions of times across the atmospheric laboratory. Here's where natural physics surpasses human engineering completely. Every droplet in the rainbow cloud produces exactly the same wavelength separation simultaneously. Perfect synchronization without any coordination mechanism. No central control system. No communication between droplets. Just fundamental physics operating identically in billions of microscopic laboratories floating in perfect formation across the sky. The rainbow you see represents the combined light show from millions of individual prism experiments all operating in harmony. Each droplet contributes its own tiny slice of spectrum. Together they create that magnificent continuous band of flowing color that spans the heavens. Nature performs Newton's revolutionary experiment on a scale that transforms the entire atmosphere into the universe's most spectacular physics demonstration. Your eyes operate the most sophisticated color laboratory on Earth using just 3 basic ingredients. Millions of microscopic sensors packed into your retina work like cosmic bartenders. They mix 3 simple recipes to create every single color experience in your visual universe. Red sunset, green forest, blue ocean, all generated by the same 3-ingredient color factory that's been operating behind your eyes since birth. Scientists call these microscopic workers cone cells. Each one smaller than a grain of pollen. Your retina contains roughly 6 million cone cells divided into 3 specialized teams. The first team responds primarily to long wavelengths around 570 nanometers. We call these L cones for long wavelength. They detect what your brain interprets as reddish light. The second team specializes in medium wavelengths near 535 nanometers. M cones for medium wavelength. They capture greenish illumination. The third team handles short wavelengths around 420 nanometers. S cones for short wavelength. They register bluish radiation. Here's where the magic happens. These three cone types don't actually see red, green, and blue directly. Instead, they measure how much their preferred wavelength appears in any incoming light beam. Like three different thermometers measuring the same temperature from different perspectives. Your brain compares the readings from all three cone teams. Then it calculates what color experience to create based on their combined reports. Orange light activates L cones strongly and M cones moderately while leaving S cones relatively quiet. Your brain interprets this specific activation pattern as orange. Yellow light stimulates both L cones and M cones equally while barely affecting S cones. Purple light excites both L cones and S cones while leaving M cones inactive. Every possible color combination results from different ratios cone cell activation across these three basic channels. The system works so efficiently that you never notice the underlying mechanics. Your conscious experience feels like seeing actual colors floating in the external world. But colors exist only inside your skull, generated by neural computation from three wavelength measurements. The rainbow you see represents your brain's interpretation of electromagnetic radiation, not electromagnetic radiation itself. Most remarkably, this three-ingredient system can distinguish roughly 10 million different color combinations. Three simple cone types. 10 million possible color experiences. Your visual system performs computational magic that creates infinite variety from minimal hardware. Like a cosmic chef preparing endless menu options using just salt, pepper, and garlic. Mother Nature plays genetic roulette with color vision using a system that would make any casino jealous. The genes controlling your cone cells live on the X chromosome. Women carry 2 X chromosomes, men carry only 1. This simple difference creates a color vision lottery where men face dramatically worse odds than women for experiencing the full rainbow spectrum. The most common color vision deficiency affects red and green discrimination. The genetic instructions for L cones and M cones sit very close together on the X chromosome. Sometimes during genetic reproduction, these instructions get scrambled, crossed wires, mixed signals. The result produces cone cells that respond to nearly identical wavelengths instead of their normal separate ranges. Men with scrambled L cone M cone genes can't distinguish red from green effectively. Both wavelength ranges activate the same cone response. Their brain receives nearly identical signals from both red and green light sources. Like trying to distinguish vanilla from vanilla in a cosmic ice cream shop. The flavors taste identical because the taste buds respond identically. Women rarely experience red-green color blindness because they carry backup genetic instructions on their second X chromosome. Even if one exome contains scrambled cone genes, the other X chromosome usually provides correct instructions. Their cells can choose which genetic recipe to follow. Men have no backup plan. One scrambled X chromosome means lifetime color vision differences. Roughly 8% of men and 0.5% of women experience some form of red-green color confusion. That's approximately 13 million American men who see rainbows differently from the majority population. They're not blind to colors. They simply organize wavelength information using different neural categories. Their rainbow contains fewer distinguishable regions between red and green portions of the spectrum. Interestingly, some forms of color vision difference provide advantages that normal color vision can't match, People with red-green differences sometimes detect camouflaged objects more easily than people with typical color vision. Military studies found that color-deficient soldiers could spot hidden equipment that remained invisible to normally sighted observers. Evolution may preserve color vision differences because they provide survival benefits under specific circumstances. Bees live in a psychedelic wonderland that would blow your mind completely. While humans see roughly 10 million colors, bees experience an expanded rainbow universe that includes ultraviolet wavelengths shorter than 380 nanometers. They see colors that have no names in human language. Colors that your brain couldn't process even if your eyes could detect them. The bee version of reality makes human color vision look like black and white television. Bee eyes contain 4 types of color-detecting cells instead of our measly 3. Their 4th cone type responds to ultraviolet wavelengths between 300 and 400 nanometers. This gives bees access to an entire section of the electromagnetic spectrum that remains forever invisible to human observers. Like having a secret 4th primary color that unlocks millions of additional color combinations. What does ultraviolet color look like? Humans can't even imagine it properly. Our brains lack the neural wiring to process UV wavelength information. It's not purple or blue or any extension of visible colors. UV represents a completely separate category of electromagnetic sensation. Like trying to describe the color of happiness or the texture of Thursday, our language contains no adequate descriptions. Flowers exploit UV vision with remarkable sophistication. Many blossoms that appear uniformly colored to human eyes display elaborate UV patterns visible only to insect pollinators. White petals may contain UV stripes pointing toward nectar sources. Yellow flowers might feature UV landing strips that guide bees to pollen deposits. Red roses could display UV warning signals that communicate no nectar here in bee language. Birds, reptiles, and many other animals possess similar UV vision capabilities. They inhabit a visual universe enriched with wavelength information that humans cannot access. We're essentially colorblind compared to most other species, living in a reduced spectrum reality while assuming we see the complete picture. Some humans gain temporary UV vision after cataract surgery. The natural lens in human eyes filters out most UV radiation. Artificial lens implants sometimes lack this filtering. Patients report seeing new colors that don't match any previous visual experience. They describe UV light as whitish blue or silvery violet, but admit these descriptions fail completely. Human language evolved to describe only human visible wavelengths. Women consistently demolish men in color discrimination contests using genetic advantages that evolution carefully preserved across millions of years. The same X chromosome system puts men at risk for color blindness. It also provides women with enhanced color vision that most people never realize exists. Nature's gender-based color vision lottery heavily favors the X chromosome combination. The genetic advantage stems from X chromosome inactivation in female cells. Women carry 2 X chromosomes with potentially different versions of cone cell genes. During development, each cell randomly chooses which X chromosome to follow for cone cell construction. Some retinal cells use the first X chromosome's cone instructions. Other cells follow the second X chromosome's genetic recipe. The result creates a mosaic retina with enhanced wavelength discrimination. This genetic mosaic effect works particularly well for L cone and M cone development. Women often inherit slightly different versions of red-sensitive and green-sensitive cone genes on their 2X chromosomes. Their retina contains cone cells tuned to subtly different wavelength ranges within the red-green spectrum region, like having both regular and fine-tuned color detectors operating simultaneously in the same visual system. Research studies consistently demonstrate female advantages in color naming, color memory, and color discrimination tasks. Women identify more color categories within the red-orange-yellow spectrum. They detect smaller wavelength differences between similar hues. They remember color information more accurately across longer time periods. These advantages appear across different cultures and age groups. Some women may possess a fourth type of functional cone cell, creating tetrachromatic vision. Instead of the normal 3-cone system, they operate 4-cone color laboratories with enhanced discrimination throughout the entire visible spectrum. Estimates suggest 12% of women carry genetic variations that could support tetrachromatic color processing, though most remain unaware of their enhanced visual capabilities. The evolutionary advantage probably relates to food gathering and offspring care responsibilities. Superior color vision helps identify ripe fruits, detect subtle changes in skin color that indicate illness, and notice environmental changes that affect family welfare. Cultures that developed superior female color discrimination likely enjoyed survival benefits across thousands of generations. Modern society largely ignores these gender-based vision differences. Color-critical industries like fashion, interior design, and visual arts could benefit from recognizing female color vision advantages. Instead, these fields often assume everyone sees colors identically, missing opportunities to leverage natural human diversity in visual processing capabilities. Your personal rainbow remains locked inside your skull where nobody else can visit. Even people with identical cone cell genetics experience subtly different color worlds. This depends on variations in neural processing, cone cell density, and brain interpretation algorithms. The red you see may not match the red your best friend experiences. Yet neither of you will ever know because color experiences can't be shared or compared directly. Individual cone cell sensitivity varies significantly between people with otherwise normal color vision. Your L cones might get 5 and 65 nanometers while your friend's L cones peak at 575 nanometers. This tiny 10 nanometer difference shifts color boundaries throughout the entire red, orange, yellow spectrum. Colors you call orange might appear more reddish to your friend's visual system. What looks yellow to you could seem more greenish to their eyes. Cone cell density also varies dramatically between individuals. Some people pack twice as many cone cells into their retinal space compared to others. Higher cone density provides finer color discrimination and more precise wavelength detection, like the difference between standard definition and high-definition television. Both display the same basic information, but one provides much more detailed resolution. Age changes color perception in predictable ways. The natural lens in your eye gradually yellows over time, filtering out more blue and violet wavelengths each decade. Colors that appeared vivid and cool during childhood slowly become warmer and more muted with age. Elderly people often prefer brighter, more saturated colors. Their aged visual system requires stronger stimulation to achieve the same color experience they enjoyed during youth. Cultural exposure influences color perception through learned associations and attention patterns. People raised in environments with rich color diversity develop more sophisticated color vocabularies and finer discrimination abilities. Artists, gardeners, and fashion designers often surpass normal population averages in color-related tasks through sustained practice and attention to subtle wavelength differences. Brain differences create the most fascinating individual variations in color experience. Some people automatically associate specific colors with particular emotions, temperatures, or spatial locations. Others experience synesthesia, where colors trigger taste sensations or musical tones. These cross-sensory connections create unique personal color realities that can't be reproduced or fully understood by others. The philosophical implications are staggering. Language allows us to coordinate color names and color categories across the human population. We all agree to call certain wavelengths blue and other wavelengths red, but the actual subjective experience of blueness or redness remains trapped within individual consciousness. Your internal color movie may differ dramatically from everyone else's internal color movie. Yet we'll never know because subjective experiences resist objective comparison. Something strange happened between Newton's first rainbow experiments and his final published color theory. The man who initially saw 5 natural color regions flowing seamlessly across his laboratory wall later convinced himself that nature preferred 7 distinct categories. This wasn't gradual scientific refinement. This was a complete conceptual makeover that transformed rainbow classification forever. Newton's early notebooks from 1666 describe exactly what any honest observer sees when splitting white light through a prism. 5 broad color regions: red, yellow, green, blue, violet. He drew diagrams showing these 5 zones blending naturally into each other without sharp boundaries. No mention of orange as a separate category. No indication that indigo deserved independent status. Just 5 flowing color territories occupying the visible spectrum. But by 1704, when Newton published his monumental work Optics, his rainbow had mysteriously grown by 2 additional colors. Orange appeared between red and yellow. Indigo materialized between blue and violet. Newton offered no explanation for these new additions, no experimental evidence supporting 7 categories over 5. No justification for the sudden expansion of his color vocabulary. The transformation reflects Newton's obsession with cosmic harmony rather than careful observation. He desperately wanted light to mirror the mathematical perfection he found in musical scales. 7 musical notes created octaves that pleased human ears. Therefore, 7 color notes should create optical octaves that pleased human eyes. Newton forced nature to match his aesthetic preferences rather than accepting what nature actually demonstrated. Newton's 7-color framework succeeded through cultural authority rather than scientific accuracy. He was Europe's most celebrated scientist. His mathematical achievements in physics and astronomy made him nearly godlike among intellectuals. When Newton declared that rainbows contained 7 colors, European scholars accepted his classification without question. Who would dare argue with the man who explained planetary motion and invented calculus? The 7-color system spread across the globe through European cultural dominance. Colonial expansion, missionary work, and educational systems exported Newton's rainbow classification to every continent. Local color traditions that had developed over thousands of years suddenly faced competition from Newton's European framework. Many indigenous color vocabularies disappeared as Western education systems imposed seven-color orthodoxy on traditional cultures. By the 20th century, Newton's arbitrary seven-color division had become scientific gospel taught in schools worldwide. Children memorized red, orange, yellow, green, blue, indigo, violet without ever learning that this sequence represented one man's personal aesthetic choice rather than objective natural law. Newton's cultural programming proved so successful that most people today can't imagine rainbows containing any number of colors other than seven. Russian speakers see rainbows that English speakers literally cannot perceive. Not because Russian eyes detect different wavelengths, not because Russian brains process light differently, but because Russian language contains two completely separate words for wavelengths that English lumps together under the single category blue. This linguistic difference creates genuine perceptual advantages that English speakers can barely comprehend. English treats all wavelengths from roughly 450 to 490 nanometers as variations of one basic color called blue, dark blue, navy blue, sky blue, all considered modifications of the same fundamental category. Russian language operates completely differently. It contains two distinct basic color terms with no overlapping territory. Goluboy covers light blue wavelengths. Sini covers dark blue wavelengths. These aren't adjective-modified versions of one color. They're separate color categories as distinct as English red and orange. This linguistic difference creates measurable perceptual effects. Russian speakers distinguish between Goluboy and Sini wavelengths faster than English speakers distinguish between light blue and dark blue wavelengths. Their brains process the two blue categories as fundamentally different colors rather than as variations of one basic color. Language literally reshapes visual processing at the neural level. Russian rainbow traditions reflect this linguistic advantage. Traditional Russian rainbow songs include 8 colors instead of Newton's 7. Goluboy and Sini both appear in the standard sequence as separate rainbow bands. Russian children learn to see 8 distinct color regions, where English-speaking children see only 7. The additional color category creates richer rainbow experiences that English speakers miss completely. The perceptual differences extend beyond rainbow observation. Russian speakers detect subtle blue range wavelength differences that English speakers overlook. They remember blue color variations more accurately. They describe blue spectrum scenes with greater precision and detail. Having 2 separate blue categories provides linguistic tools that enhance blue-related visual processing across all contexts. Other languages create similar effects with different color ranges. Some cultures distinguish multiple green categories that English treats as one basic color. Others separate what English calls red into distinct warm and cool categories. Each linguistic division potentially creates perceptual advantages within specific wavelength ranges. The implications challenge Western assumptions about universal color perception. Newton's 7-color system dominates global color education, but alternative linguistic frameworks might provide superior color discrimination within specific spectral regions. Russian 8-color rainbows represent just one example of non-Western color wisdom that English speakers have overlooked for centuries. Ancient Japanese culture solved the rainbow puzzle using a completely different approach that would puzzle Western color theorists. Instead of dividing the spectrum into 7 distinct categories like Newton, Traditional Japanese recognized 6 rainbow colors. They treated blue and green as one fundamental category called ao. This wasn't primitive color confusion. This was sophisticated color philosophy that organized wavelengths according to principles Newton never considered. The concept of O encompasses wavelengths from roughly 450 to 550 nanometers, what English speakers rigidly separate into blue and green territories. Japanese traditionally viewed as different expressions of one underlying color essence. Ocean water and forest leaves both displayed a characteristics despite their obvious wavelength differences. The linguistic framework emphasized color relationships rather than color boundaries. This integrated blue-green category created 6 color rainbow traditions that persisted for over 1,000 years. Traditional Japanese rainbow songs included red, orange, yellow, ao, indigo, and violet. The O category covered what Western observers would describe as both blue and green portions of the spectrum. Japanese children learned to see flowing color transitions, where Western children learned to see sharp categorical boundaries. Modern Japanese demonstrates the cultural power of Western color influence. Contemporary Japanese contains separate words for blue, buru, and green, gurian, borrowed from English. Young Japanese speakers increasingly adopt Western color categories that their ancestors would have found unnecessarily rigid. The traditional O framework survives mainly in cultural contexts like poetry, art, and ceremony. But traditional O thinking offers insights that Western color theory misses completely. The blue-green spectral region contains the most wavelengths that human eyes can distinguish. Dividing this rich territory into just 2 categories wastes much of the discriminatory potential that human vision provides. The O framework encouraged attention to subtle wavelength relationships that rigid blue-green boundaries discourage. Traffic light systems in Japan reveal the ongoing cultural tension between traditional and Western color frameworks. Japanese traffic signals use blue-green lights that technically qualify as O under traditional color classification. English speakers would call these lights green, but Japanese speakers often describe them as O rather than the borrowed word gurian. The lights occupy the borderland between traditional and modern color vocabularies. Scientific studies suggest that traditional O classification might provide perceptual advantages for certain visual tasks. People trained to see blue-green wavelengths as related categories sometimes detect subtle environmental changes that escape observers using rigid blue-green boundaries. Traditional Japanese color wisdom recognized wavelength relationships that Western color theory treats as separate territories. Deep in the Amazon rainforest lives a tribe that would completely baffle Newton's color theories. The Para people recognize only 3 basic color categories across the entire visible spectrum. Not 7 like Newton, not 8 like Russians, not 6 like traditional Japanese. Just 3 fundamental color divisions that organize all wavelength information into the simplest possible framework. Pyrocolor vocabulary contains words that roughly translate as light, dark, and red. The light category encompasses what English speakers separate into white, yellow, orange, and light green. The dark category includes black, blue, purple, and dark green. The red category covers wavelengths that English speakers distinguish as red, pink, and brown. 3 categories capture all human color experience according to Para cultural logic. This minimal color framework doesn't indicate visual deficiency or cultural poverty. Pyra people demonstrate normal color discrimination abilities when tested with standard color vision assessments. Their eyes detect the same wavelength differences that anyone else sees. Their brains process color information identically to people from cultures with elaborate color vocabularies. The difference lies entirely in how they organize and discuss color experiences linguistically. Pyra rainbow traditions reflect their three-category system. When rainbows appear over their forest territory, Pyra observers describe seeing three flowing regions of light, dark, and red wavelengths. They don't subdivide these regions into smaller color territories. The entire visible spectrum organizes into just three meaningful categories that serve all their cultural color needs. The Pyra approach challenges fundamental assumptions about human color perception. Western color theory assumes that more color categories automatically provide better color discrimination and more sophisticated color awareness. The Pyra demonstrate that highly functional color systems can operate with minimal categorical structure. Three categories suffice for all practical color communication within their cultural context. Anthropologists studying Pyra color cognition discovered unexpected advantages to their simplified system. Pyra speakers show no confusion about which color category applies to any particular wavelength. English speakers sometimes disagree about borderline cases between blue and green or orange and red. The Pyra three-category system eliminates such boundary problems by creating much broader color territories with unambiguous membership rules. The Pyra also demonstrate remarkable flexibility in adopting alternative color frameworks when circumstances require them. Individual tribe members who learn Portuguese or other languages readily acquire additional color categories for cross-cultural communication, but they return to three-category thinking for internal tribal discussions. Their color system adapts to social context rather than imposing rigid categorical requirements. Newton harbored a secret obsession that would seem bizarre to modern scientists. He desperately wanted to prove that light wavelengths corresponded directly to musical notes in perfect mathematical harmony. This wasn't casual scientific curiosity. This was deep spiritual conviction that the universe operated according to divine proportions connecting all natural phenomena through elegant mathematical relationships. The musical connection seemed obvious to Newton's 17th century mindset. Musical scales contained 7 notes that created pleasing harmonic progressions. Light spectrums contained wavelengths that created pleasing visual experiences. Surely these parallel structures reflected identical mathematical principles operating across different sensory domains. God wouldn't create 2 separate organizational systems when one unified system could govern both sound and light simultaneously. Newton spent months trying to map specific light wavelengths onto specific musical frequencies. He calculated ratios between adjacent colors that might match ratios between musical intervals. Red light should correspond to the musical note C, orange should match D. Yellow should align with E. The entire rainbow should sing in perfect chromatic harmony with mathematical precision that would reveal divine truth about cosmic organization. The mathematical relationships refused to cooperate with Newton's spiritual vision. Light wavelengths follow completely different physics than sound waves. Light frequencies span the electromagnetic spectrum at rates of hundreds of trillions of cycles per second. Musical frequencies operate in the acoustic range of hundreds to thousands of cycles per second. The scales differ by factors of billions. No simple mathematical ratios connect light colors to musical notes. But Newton's musical rainbow theory shaped his 7-color classification in profound ways. He needed exactly 7 color categories to match the 7-note musical scale. His original 5-color observations didn't fit the musical template, so he invented orange and indigo to create the magical number 7. The additional colors existed primarily to satisfy Newton's cosmic harmony requirements, rather than to describe actual optical phenomena. Newton's musical color theories influenced European aesthetics for centuries. Artists, architects, and designers assumed that colors should harmonize according to musical principles. Color wheels organized wavelengths to mirror musical intervals. Interior decorators chose color combinations that supposedly created visual music for the eyes. These aesthetic traditions persist in modern design education despite having no scientific foundation. The irony is magnificent. Newton's completely wrong musical color theory accidentally created the 7-color rainbow system that dominates global color education today. His mistaken belief in light-sound correspondence gave the world its standard rainbow vocabulary. Scientific error became cultural truth through the power of Newton's intellectual authority. Modern physics reveals genuine connections between electromagnetic radiation and mechanical vibrations that Newton could never have imagined. Atoms emit light when electrons transition between energy levels that vibrate at specific frequencies. But these quantum mechanical relationships operate at scales and frequencies far removed from human perception of colors and musical notes. The universe does contain mathematical harmonies connecting light and sound, but they're vastly more complex and subtle than Newton's simple wavelength-to-note correspondences. Newton's musical rainbow represents one of science history's most beautiful mistakes. Wrong physics led to lasting cultural influence that shaped human color perception across the entire planet. Sometimes scientific errors prove more powerful than scientific truths for organizing human experience and understanding. Most people assume rainbows only appear during daylight hours. They assume the sun provides adequate illumination for spectacular color displays. But nature operates a secret nighttime rainbow service. Most humans never discover it. Under perfect conditions, the full moon generates enough reflected sunlight. Ethereal silver rainbows float like cosmic ghosts across darkened skies. Moonbows require extraordinary atmospheric timing. It occurs maybe 5 nights per month when lunar conditions align properly. The moon must be nearly full to provide sufficient illumination. Less than 90% lunar illumination produces too little light for rainbow generation. The moon must also occupy a low position in the sky. High overhead positions create wrong geometric angles for rainbow formation. These requirements limit moonbow opportunities. They last a few hours during specific nights each month. The physics operates identically to daytime rainbows, but the light intensity is dramatically reduced. Moonlight enters water droplets suspended in night air. Different wavelengths bend by different amounts according to their refractive properties. Red light exits droplets at 42 degrees. Violet light emerges at 40 degrees. The complete color spectrum spreads across the night sky. It does so exactly like daytime rainbow displays. But human eyes struggle to detect moonbow colors under low light conditions. The cone cells responsible for color vision require relatively bright illumination. Rod cells that dominate night vision detect light intensity. They do not provide color information. Most people see moonbows as silvery white arcs. Their eyes cannot process the faint color signals. Those signals definitely exist in the moonlight spectrum. Long exposure photography reveals the hidden truth about moonbow colors. Camera sensors can accumulate light over extended time periods. Human eyes cannot match that. Photographs of moonbows show surprisingly vivid reds, oranges, yellows, greens, blues, and violets. The complete rainbow palette appears in nighttime images, but it stays invisible to direct human observation. Nature creates full-color moonbows. Our visual system simply cannot appreciate them properly. The best moonbow locations feature consistent weather patterns. They produce frequent rain showers combined with clear skies. Hawaii's windward coasts experience ideal conditions. Trade wind patterns create regular nighttime precipitation. Clear lunar visibility remains. Victoria Falls in Africa generates permanent water mist. It creates moonbow opportunities whenever the full moon rises in the proper position. Most people live entire lifetimes without witnessing a single moonbow. The viewing requirements are so restrictive. You need full moon illumination and active precipitation. You also need clear skies behind you and rain clouds in front of you. You need the patience to stay awake during optimal nighttime hours. Miss any component, and the moonbow opportunity vanishes. It stays gone until the next lunar cycle creates another brief window of possibility. Winter transforms the entire atmosphere into a cosmic crystal palace. Millions of floating ice prisms create optical magic. It rivals any rainbow display. High-altitude clouds contain hexagonal ice crystals. They function as precision optical instruments. They are scattered across miles of frozen sky. These microscopic ice factories generate light phenomena. Most people mistake them for weather effects. They do not recognize them as sophisticated physics demonstrations. The most spectacular ice crystal display creates multiple false suns. They are called sun dogs or perhelia. These brilliant light spots appear exactly 22 degrees left and right of the real sun. This happens when atmospheric conditions achieve perfect crystal alignment. The fake suns shine with rainbow colors. The colors shift from red near the actual sun to blue at the outer edges. Sometimes the false suns appear brighter than the real sun. They create three-sun skies that would have terrified ancient civilizations. The 22-degree angle results from hexagonal ice crystal geometry. It operates according to precise optical laws. Sunlight enters one face of a hexagonal ice crystal. It exits through an adjacent face. The light beam bends by exactly 22 degrees. Millions of ice crystals float in random orientations throughout high clouds. They perform this identical bending simultaneously. The collective result creates circular halos. It also creates bright sun dog spots. They appear exactly where crystal physics predicts they should appear. Ice crystal halos extend far beyond simple 22-degree circles. Under optimal conditions, the frozen atmosphere generates complex geometric patterns. These include 46-degree halos and circumhorizontal arcs. They also include tangent arcs and complete circular rainbows. These are called circumzenithal arcs. The entire sky becomes a crystalline light laboratory. It displays multiple simultaneous optical phenomena. They intersect and overlap in patterns of extraordinary mathematical beauty. Plate-shaped ice crystals create different optical effects than column-shaped ice crystals. Plate crystals tend to fall with their flat faces horizontal. They create horizontal light pillars. These extend vertically above and below the sun. column crystals tumble randomly through the atmosphere. They generate circular halos and sundog displays. The ice crystal shapes determine which optical phenomena appear. They determine it at any particular moment in the winter sky. Aircraft pilots regularly witness crystal displays. Ground observers never see them. Flying through high-altitude cirrus clouds places pilots inside the optical laboratory. Ice crystals perform their light-bending magic there. From this perspective, halos and sundogs appear with intensity and clarity. Ground observation cannot match it. The cockpit becomes a front-row seat. It is for atmospheric optics, shows that most humans miss completely. Fog creates one of nature's most paradoxical optical phenomena. It seems to violate everything we know about rainbow formation. Instead of producing magnificent color displays, fog generates completely white rainbows. They are called fog bows. They contain no visible colors whatsoever. These ghostly white arcs challenge our understanding. They challenge how light wavelengths interact with water droplets. They challenge how spectral displays are created. The mystery lies in droplet size differences. They fundamentally alter how light interacts with suspended water spheres. Traditional rainbows require water droplets. They are roughly 0.5 to 5 millimeters in diameter for optimal color separation. Fog contains much smaller droplets. They typically measure less than 0.05 millimeters across. These microscopic water spheres create completely different optical physics. They produce white light instead of rainbow colors. Small fog droplets generate light scattering. They do not generate light refraction. Tiny fog droplets scatter all wavelengths equally in all directions. They do not bend different wavelengths by different amounts like large raindrops. Red light scatters identically to blue light. Orange wavelengths behave exactly like violet wavelengths. The equal scattering eliminates color separation. It produces uniform white illumination across the entire arc. Wave interference effects become dominant. This happens when water droplets approach the same size as light wavelengths themselves. Fog droplets measuring about 1/100th to 1/10th of a millimeter interact with visible light wavelengths. Those wavelengths measure about 4 to 7 ten-thousandths of a millimeter. This happens through complex wave physics. It does not happen through simple geometric optics. The light waves interfere with themselves. They do so as they pass around the tiny water spheres. This creates diffraction patterns. They wash out color information. Fog bows appear much broader than traditional rainbows. The small droplet physics spreads light across wider angular ranges. Normal rainbows occupy roughly 2-degree wide arcs across the sky. Fog bows can extend 5 to 10 degrees in width. The broad white band creates a ghostly appearance. It seems to float mysteriously in the fog bank. It has no obvious connection to sunlight or water droplets. The best fogbow viewing occurs in maritime environments. Ocean fog banks provide ideal droplet size distributions. Coastal mountains experience optimal conditions. Fog flows inland during morning hours. Bright sunlight illuminates the fog bank from behind. The observer must position themselves between the sun and the fog. The sun must be at their back for proper fogbow geometry. Key: airplane passengers sometimes witness spectacular fogbows. This happens when flying just above fog layers that extend below the aircraft. From this elevated perspective, fogbows can appear as complete white circles. They surround the airplane's shadow on the fog surface below. The circular geometry reveals the true shape. It is the true shape of all rainbow phenomena. Ground observers see only partial arcs. Certain locations on Earth operate 365-day rainbow services. They never close for weather or seasonal changes. Major waterfalls generate continuous water mist. It creates permanent rainbow installations. These are visible during any sunny period throughout the entire year. These natural rainbow factories represent the most reliable rainbow viewing opportunities. They are on the planet. Niagara Falls generates rainbow displays. They have operated continuously for thousands of years. The massive water flow creates consistent mist clouds. They hover near the waterfall base regardless of weather conditions. During any sunny period, multiple rainbows appear simultaneously in the mist zone. Primary rainbows, secondary rainbows, supernumerary rainbows. The waterfall mist provides perfect droplet conditions. Traditional weather rarely achieves that. The physics advantages of waterfall rainbows stem from consistent droplet size and density. Weather-dependent rainbows cannot match that. Natural rainstorms produce droplets of varying sizes. They fall at different speeds. They create irregular mist patterns. Waterfall mist contains uniformly sized droplets. They remain suspended at consistent altitudes. The stable droplet environment generates more vivid and persistent rainbow displays. Atmospheric precipitation cannot provide that. Victoria Falls in Africa creates rainbow conditions so reliable. Local tourism operates scheduled rainbow viewing tours. The waterfall generates mist clouds. They are visible from 20 kilometers away during dry season. Water flow concentrates into narrower channels then. Peak rainbow conditions occur during afternoon hours. The sun angle optimizes geometric relationships between sunlight, mist, and observer positions. Yosemite Falls produces seasonal rainbow displays. They appear during spring snowmelt. Maximum water flow generates the densest mist clouds then. The waterfall orientation creates ideal solar geometry. It does so during late afternoon hours. Sunlight penetrates the valley at optimal angles for rainbow formation. Photographers travel worldwide. They do it specifically to capture Yosemite's predictable rainbow displays. These combine waterfall grandeur with reliable rainbow optics. Smaller waterfalls can generate surprisingly spectacular rainbow effects. This happens when geometric conditions align properly. Garden sprinklers demonstrate the same physics principles. They do so on miniature scales. Any water source that creates fine mist in bright sunlight can produce rainbow displays. It can, given proper viewing angles and atmospheric conditions. The reliability of waterfall rainbows makes them ideal for scientific rainbow research. It requires consistent observational opportunities. Researchers study rainbow physics and droplet interactions. They also study color perception. They often conduct experiments at waterfall locations. Rainbow displays can be observed repeatedly there under controlled conditions. Natural weather produces too much variability. It does so for systematic rainbow studies. Waterfall rainbow viewing requires specific timing and positioning. It maximizes geometric advantages. The sun must illuminate the mist from behind the observer. Morning and afternoon hours provide optimal solar angles. Midday conditions often position the sun too high overhead. That breaks proper rainbow geometry. Wind direction affects mist patterns and rainbow visibility. Calm conditions preserve mist formation. Strong winds disperse droplets too quickly for stable rainbow displays. Every rainbow you've ever seen from the ground represents just half of a complete circular light show. The circle extends below the horizon. Earth blocks your view. The full rainbow geometry creates perfect circles. They are centered around the point directly opposite the sun. Only observers elevated high enough can see past Earth's curvature. They can witness the complete circular rainbow that nature actually produces. Aircraft passengers occasionally witness one of optics' most spectacular phenomena. It happens during flights through or above rain cloud systems. The sun shines from behind the aircraft into water droplets ahead. Complete circular rainbows surround the airplane's shadow. The shadow is projected onto cloud layers below. The circular rainbow displays the true geometry. Ground-based observers never experience it. The physics creates identical wavelength separation. It does so at every point around the complete circle. Red light emerges from droplets at exactly 42.3 degrees from the antisolar point. This is true regardless of compass direction. The circular pattern results from spherical geometry. It operates consistently in all directions around the central axis. Ground observers see only the top portion of this circular pattern. Earth's surface interrupts the bottom half. Glory phenomena accompany complete circular rainbows. This happens under optimal viewing conditions. The airplane's shadow appears surrounded by concentric rings of brilliant color. They are called optical glories. These colored rings result from light wave interference effects. They occur when aircraft shadows interact with uniformly sized cloud droplets. The combination of circular rainbows and optical glories creates spectacular displays. Pilots and passengers remember them for lifetimes. Mountain climbers standing on high peaks sometimes glimpse partial circular rainbow displays. Weather conditions position rain clouds below their elevation. The additional altitude allows observers to see further below the normal horizon. It reveals more of the complete circular geometry. But even mountain peak observations rarely show more than 3/4 of the complete circle. Hot air balloon passengers enjoy unique opportunities. They can witness circular rainbows from positions that combine adequate altitude with slow movement speeds. That allows extended observation periods. Balloon baskets provide stable observation platforms. Commercial aircraft cannot match them for rainbow photography. The quiet balloon environment eliminates engine noise and vibration. They interfere with detailed rainbow observation. Helicopter pilots report spectacular circular rainbow encounters. This happens during search and rescue operations. They require flight through storm systems. The helicopter's ability to hover in position allows extended observation. It allows extended observation of circular rainbow displays. Fixed-wing aircraft pass through too quickly. Emergency medical pilots develop expertise. They predict atmospheric conditions that generate circular rainbow opportunities. The rarity of complete circular rainbow observations makes them among the most sought-after natural phenomena. They are for serious rainbow enthusiasts. Most people never witness more than partial arcs. They do so during their entire lifetimes. Complete circular rainbows require specific combinations. They require altitude, weather, lighting, and observer position. These align maybe once per decade for frequent airline passengers. Photography of complete circular rainbows presents unique technical challenges. Wide-angle lenses are required to capture the full circle. They create distortion. It alters the rainbow's natural appearance. Multiple exposures combined into composite images can preserve accurate geometry. They can capture the complete circular display, but single-frame circular rainbow photographs remain extremely rare. They are rare even among professional atmospheric optics photographers. Beyond the violet edge of human vision lies a vast electromagnetic empire. It would revolutionize rainbow experiences if your eyes could access it. The ultraviolet realm stretches from 380 nanometers down to 100 nanometers. It contains roughly 3 times more wavelength territory than the entire visible spectrum humans can detect. This invisible rainbow extension operates according to identical physics principles while remaining forever locked away from direct human observation. Ultraviolet wavelengths carry significantly more energy than visible light. That is because shorter wavelengths pack more electromagnetic punch per photon. UV irradiation from 380 to 315 nanometers possesses enough energy to trigger chemical reactions in human skin. These reactions create tanning effects. UVB radiation from 315 to 280 nanometers carries sufficient energy to damage DNA molecules. It can cause sunburn. UVC radiation below 280 nanometers packs so much energy that Earth's ozone layer must filter it completely. This prevents sterilization of surface life. The invisible UV rainbow contains spectral features that would appear absolutely magnificent if human eyes possessed the necessary detection equipment. Many flowers display elaborate ultraviolet patterns completely hidden from human observation. What appears as a uniform yellow sunflower to human eyes reveals intricate UV landing strips and nectar guides. This happens when it is photographed with UV-sensitive cameras. The hidden patterns create a parallel floral universe of extraordinary beauty that exists right under our noses. UV photography reveals that the sky itself contains rainbow features invisible to normal human perception. Atmospheric gases scatter ultraviolet wavelengths differently than visible wavelengths. This creates UV color gradients and patterns that change throughout the day. They shift according to solar angle and atmospheric conditions. The invisible UV sky displays a constantly shifting rainbow that no human has ever witnessed directly. Specialized UV cameras developed for scientific research can translate ultraviolet wavelengths into visible colors. These visible colors approximate what UV vision might experience. These false color images reveal that familiar environments contain hidden UV rainbow landscapes of extraordinary complexity. Ordinary gardens transform into alien wonderlands covered with geometric patterns and color contrasts. They also reveal design elements completely invisible to an augmented human vision. The ozone layer acts as Earth's UV rainbow filter. It selectively blocks the most energetic wavelengths while allowing less dangerous UVA radiation to reach the surface. This natural filtering system protects life from lethal ultraviolet sterilization. It also permits enough UV penetration to enable vitamin D synthesis in human skin. Without ozone protection, the full ultraviolet rainbow would prove fatal to most surface organisms within hours of exposure. High-altitude locations provide enhanced UV rainbow experiences that lowland areas cannot match. Mountain peaks above 3,000 meters receive dramatically more UV radiation. Thinner atmosphere provides less filtering protection. Mountaineers often experience severe sunburn despite cool temperatures. The invisible UV rainbow intensifies with altitude in ways that visible light does not. On the opposite side of the visible spectrum lies an enormous electromagnetic territory. Here, rainbow colors transform into heat signatures that tell temperature stories about everything in your environment. The infrared realm extends from 700 nanometers all the way out to 1 millimeter wavelengths. It encompasses a spectral empire roughly 1,000 times larger than human visible range. This thermal rainbow operates continuously around you. It broadcasts temperature information that specialized detection equipment can translate into spectacular heat-based color displays. Every object warmer than absolute zero emits infrared radiation according to its temperature. Your body radiates infrared wavelengths around 10,000 nanometers. That corresponds to your 98.6-degree internal temperature. Hot coffee emits shorter infrared wavelengths around 3,000 nanometers. Ice cubes broadcast longer infrared wavelengths near 15,000 nanometers. The invisible heat rainbow provides a complete thermal inventory of your surroundings. It updates continuously as temperatures change throughout the day. Thermal imaging cameras reveal the hidden infrared rainbow that surrounds you constantly. These devices translate heat radiation into false color images. Different temperatures appear as different rainbow colors. Hot objects glow white, yellow, and red in thermal images. Cool objects appear blue, purple, and black. The result creates heat-based rainbow landscapes that look like psychedelic art. They actually represent precise temperature measurements of everything in the camera's field of view. The infrared rainbow spectrum divides into three main regions with different practical applications. Near-infrared from 700 to 1,400 nanometers penetrates deeply into biological tissue. It enables medical imaging that reveals blood flow patterns invisible to visible light. Mid-infrared from 1,400 to 3,000 nanometers corresponds to molecular vibration frequencies. It can identify chemical compositions through spectroscopic analysis. Far infrared from 3,000 nanometers to 1 millimeter provides thermal imaging capabilities for building energy audits. It also supports military night vision and astronomical observations. Atmospheric water vapor absorbs specific infrared wavelengths while transmitting others. This creates invisible atmospheric windows that infrared technology must navigate carefully. Weather satellites exploit these infrared transparency windows to measure cloud temperatures. They track storm development and monitor Earth's energy balance from space. The infrared rainbow provides climate information that visible light observations cannot deliver. Building energy efficiency depends heavily on infrared rainbow management that most homeowners never consider. Thermal imaging reveals heat leaks around windows, doors, and insulation gaps. These leaks waste enormous amounts of energy. The invisible infrared rainbow broadcasting from your house tells a complete story about energy efficiency. Visible inspection cannot detect it. Professional energy auditors use thermal cameras to map household heat signatures. They identify improvement opportunities. Firefighters rely on infrared rainbow detection to locate victims trapped in smoke-filled buildings where visible light provides no useful information. Thermal imaging cameras penetrate smoke and darkness. They reveal the heat signatures of people, animals, and fire hot spots that would remain invisible to normal vision. The infrared rainbow becomes a life-saving tool when all other visual information disappears. Certain predators possess natural infrared detection systems that would make human military technology weep with envy. Pit vipers, pythons, and boa constrictors hunt using specialized organs. These organs translate the invisible heat-lit rainbow into precise thermal images of their prey. These biological infrared sensors operate with sensitivity that rivals the most sophisticated thermal imaging equipment humans have ever developed. pit viper facial heat sensors contain thousands of infrared-detecting nerve endings. They are packed into organs called pit chambers located between their eyes and nostrils. Each pit chamber functions like a biological thermal camera. It creates detailed heat maps of the snake's surroundings. The infrared information combines with visual data. This produces composite sensory experiences that humans cannot imagine properly. The thermal detection sensitivity reaches extraordinary levels that surpass human infrared technology in many applications. Pit vipers can detect temperature differences as small as about 0.003 of a degree Celsius. This works at distances up to 1 meter. This thermal precision allows them to track warm-blooded prey through complete darkness. They use nothing but infrared radiation signatures. A mouse hiding motionless in pitch-black conditions remains perfectly visible to pit viper thermal sensors. Python heat detection operates through different biological mechanisms that achieve similar thermal imaging results. Pythons possess heat-sensitive scales along their lips. These scales contain infrared receptors connected directly to their brain's visual processing centers. These thermal sensors create heat-based images. They overlay with normal vision to produce enhanced predatory awareness. Pythons literally see the heat rainbow that radiates from every warm object in their environment. Vampire bats represent the most sophisticated mammalian infrared detection system known to science. Their facial heat sensors guide them to blood vessels located just beneath their victim's skin surface. The bats use infrared rainbow detection to identify optimal feeding locations. Warm blood flows closest to the surface at these points. This thermal guidance system operates with surgical precision that human medical technology struggles to match. Even some insects demonstrate infrared detection capabilities that aid their survival strategies. Certain beetles seek out forest fires where they lay eggs in freshly burned wood. Their infrared sensors guide them toward active fire zones from distances of several kilometers. The beetles navigate using the infrared rainbow signatures of burning trees to locate optimal breeding territories. Marine animals exploit infrared detection for underwater navigation that visible light cannot provide. Some deep-sea fish possess thermal sensors. These sensors detect the heat signatures of other organisms in the pitch-black ocean depths. Whale heat plumes create infrared trails that predators can follow. They can follow for hours after the whales have passed through an area. Bird migration may involve infrared navigation systems that help them follow thermal air currents during long-distance flights. Soaring birds like eagles and hawks demonstrate remarkable ability to locate rising warm air columns called thermals. Some researchers suspect these birds possess infrared sensing capabilities. These capabilities may reveal the heat rainbow signatures of optimal flight paths. Far beyond infrared radiation lies the vast electromagnetic territory of radio waves. Here, the rainbow concept explodes into cosmic proportions that dwarf all human-scale phenomena. Radio wavelengths extend from 1 millimeter all the way out to 100 kilometers. This creates a spectral empire millions of times larger than visible light. This radio rainbow carries information about cosmic processes that occurred billions of years ago. It travels across distances that challenge human comprehension. Radio telescopes function as cosmic rainbow detectors. They translate invisible electromagnetic radiation into images of astronomical objects and events that visible light observations miss completely. The famous spiral arms of galaxies appear dramatically different when observed through radio wavelengths compared to visible light photography. Radio observations reveal gas and dust structures, star formation regions, and magnetic field patterns that remain invisible to optical telescopes. Each radio wavelength provides different types of cosmic information. It is like tuning into separate cosmic radio stations broadcasting from across the universe. Hydrogen gas throughout the galaxy emits radials at exactly 21 centimeters wavelength. This hydrogen radio rainbow allows astronomers to map the structure and motion of gas clouds. These clouds will eventually collapse to form new stars. Water molecules in space broadcast radio signals at 1.35 centimeter wavelengths. These signals reveal the locations of cosmic water vapor. Pulsars represent cosmic lighthouses that broadcast radio rainbow signals with clockwork precision across thousands of light-years of space. These rapidly rotating neutron stars emit radio beams. These beams sweep across Earth like lighthouse beams every few seconds or milliseconds. Each pulsar transmits its own unique radio rainbow signature. This allows astronomers to identify individual pulsars and measure their rotation rates with extraordinary precision. 2. The cosmic microwave background represents the universe's most ancient radio rainbow. It has been traveling through space for 13.8 billion years since the Big Bang. This relic radiation preserves information about cosmic conditions when the universe was only 380,000 years old. Radio telescopes detect tiny temperature variations in this ancient radio rainbow. These variations reveal the seeds of galaxies, stars, and planets that would form billions of years later. Jupiter broadcasts powerful radio storms that early radio astronomers discovered accidentally. This happened while developing radar technology during World War II. These Jovian radio signals result from charged particles interacting with Jupiter's powerful magnetic field. The planet's radio rainbow emissions change according to the orbital positions of Jupiter's moons. This creates a complex celestial radio symphony that continues broadcasting across the solar system. Radio astronomy reveals cosmic phenomena that would remain completely unknown if astronomers relied only on visible light observations. Black holes cannot be seen directly because they emit no visible light, but matter falling into black holes generates radio emissions that reveal the presence and behavior of these invisible cosmic monsters. The radio rainbow provides the only direct evidence for many cosmic processes that shape the universe. ACTI programs search for artificial radio signals that might indicate intelligent life elsewhere in the galaxy. The radio rainbow spectrum offers vast communication channels. Extraterrestrial civilizations might broadcast messages across interstellar distances in these channels. Radio waves travel at light speed through space without significant absorption. This makes them ideal for long-distance cosmic communication that visible light cannot provide. Ancient floodwaters recede. Noah's Ark settles on solid ground. God paints the first rainbow across clearing skies as an eternal promise never to destroy the world by flood again. This biblical origin story launched the rainbow into human cultural consciousness as the ultimate symbol of divine mercy and cosmic renewal. But the rainbow's symbolic journey across 4,000 years of human civilization would prove far more complex and revolutionary than any ancient storyteller could have imagined. Medieval Christianity embraced the rainbow as God's covenant bridge connecting heaven and earth. Cathedral stained glass windows incorporated rainbow motifs to represent divine light filtering into human understanding. The 7 rainbow colors matched the 7 virtues, 7 sacraments, and 7 days of creation in perfect theological harmony. European art depicted rainbow halos around saints and angels to signify their holy connection to divine illumination. The Renaissance shattered rainbow symbolism's purely religious boundaries. Artists like Leonardo da Vinci studied rainbow optics as natural philosophy rather than divine miracle. Scientific revolution thinkers began viewing rainbows as atmospheric phenomena worthy of mathematical analysis rather than theological interpretation. The rainbow slowly transformed from religious symbol into natural wonder that revealed cosmic mechanical principles. Romanticism in the 18th and 19th centuries reclaimed rainbow symbolism for emotional and aesthetic purposes. Poets like William Wordsworth celebrated rainbows as triggers for childhood wonder and spiritual connection to nature. The rainbow became associated with imagination, creativity, and the sublime experience of natural beauty. German folklore developed rainbow bridges connecting earthly existence to mystical realms of possibility. The 20th century witnessed rainbow symbolism's most dramatic transformation. Civil rights movements adopted rainbow imagery to represent diversity, inclusion, and unity across human differences. The 1960s counterculture embraced rainbows as symbols of peace, love, and harmony with nature. Environmental movements used rainbow symbolism to represent ecological diversity and planetary stewardship. Modern LGBTQ+ movements completed the rainbow's symbolic evolution by transforming it into the universal emblem of gender and sexual diversity. Gilbert Baker's original 1978 Pride flag contained 8 rainbow colors representing different aspects of human experience. Hot pink for sexuality, red for life, orange for healing, yellow for sunlight, green for nature, turquoise for magic, blue for serenity, purple for spirit. The rainbow had journeyed from divine covenant to human celebration of infinite diversity. Today's rainbow symbolism operates simultaneously across multiple cultural meanings that would confuse ancient observers completely. Corporate logos deploy rainbow colors to signal inclusivity and progressive values. Children's products use rainbows to evoke joy and wonder. Weather forecasting apps display rainbow icons to represent improving atmospheric conditions. The same optical phenomenon that once signified God's promise now carries dozens of different cultural messages depending on context and audience. Paris, 1860s. A group of rebellious artists abandons the dark, earth-toned palettes that had dominated European painting for centuries. Armed with new scientific knowledge about light wavelengths and color mixing, these revolutionary painters explode onto canvas with brilliant rainbow colors that shock the conservative art establishment. The Impressionist movement transforms painting by applying Newton's color science directly to artistic practice. Claude Monet becomes obsessed with capturing the exact wavelength combinations he observes in natural light. His series of haystacks, water lilies, and cathedral facades document how the same objects appear completely different under various lighting conditions throughout the day. Monet essentially conducts scientific experiments with paint, testing how different color combinations create optical effects that mimic natural rainbow phenomena. The scientific color wheel, developed by Isaac Newton, provides Impressionist painters with systematic understanding of complementary color relationships. Orange paint placed next to blue paint creates visual vibrations that make both colors appear more intense. Red brushstrokes adjacent to green pigments generate optical mixing effects that create entirely new color sensations in the viewer's eye. Artists discover they can manipulate perception using color science principles. Pointillism pushes rainbow science to its logical artistic extreme. Georges Seurat and Paul Signac abandon color mixing on the palette entirely. Instead, they apply pure spectral colors in tiny dots that blend optically in the viewer's retina rather than physically on the canvas. Their paintings function as scientific demonstrations of additive color mixing that reproduce rainbow effects through systematic color placement. Vincent van Gogh develops his own rainbow-inspired color theories that prioritize emotional impact over scientific accuracy. His brilliant yellow sunflowers against blue backgrounds exploit complementary color relationships to create visual intensity that conventional earth tone palettes could never achieve. Van Gogh's rainbow-influenced color choices generate psychological effects that transform painting from representation into emotional communication. The color tube revolution enables rainbow painting techniques that previous generations couldn't attempt. Before portable paint tubes, artists mixed pigments from raw materials that limited color choices to browns, blacks, and muted earth tones. Mass-produced paint tubes provide access to brilliant synthetic pigments that approximate pure spectral wavelengths. Artists suddenly possess rainbow palettes that match the optical intensity of natural light phenomena. Post-Impressionist artists push rainbow color science toward complete abstraction. Wassily Kandinsky develops theories connecting specific colors to emotional and spiritual states. Yellow represents earthly energy, blue embodies spiritual transcendence, red signifies vital force, green suggests peaceful balance. Kandinsky's rainbow-based color psychology influences abstract art movements throughout the 20th century. Modern digital art returns to rainbow physics principles through RGB color display technology. Computer monitors recreate rainbow colors by combining red, green, and blue light wavelengths in the same additive mixing process that creates natural rainbows. Digital artists manipulate millions of color combinations that exploit the three-cone visual system that Newton could never have imagined. The rainbow's scientific principles continue driving artistic innovation 350 years after Newton's first prism experiments. Irish storytellers created history's most successful marketing campaign for an impossible product. The legend of leprechaun, gold hidden at rainbow ends, has inspired countless treasure hunters across dozens of cultures for over 800 years. This masterpiece of folklore transforms the simple physics principle that rainbows have no fixed location into humanity's most enduring treasure hunt narrative. The original Irish leprechaun legends emerged during medieval times when Ireland's economy depended heavily on cattle herding and agriculture. Rainbow appearances after storms signified returning fair weather and improved grazing conditions. Folklore connected these positive weather associations with hidden fairy treasures that could only be accessed when rainbows revealed secret portal locations. The stories provided psychological comfort during harsh economic periods by suggesting supernatural wealth remained available to those brave enough to seek it. Leprechauns evolved into master marketers who offered tantalizing product samples without ever delivering the complete treasure package. According to traditional stories, leprechauns would guide treasure seekers very close to rainbow endpoints before vanishing with their gold at the last possible moment. This narrative structure creates perfect psychological hooks that maintain customer interest while providing plausible explanations for inevitable failure to locate the promised treasures. The rainbow treasure hunt exported globally through Irish immigration patterns that scattered the folklore across continents. Irish immigrants brought leprechaun stories to America, Australia, Canada, and other destinations where local cultures adapted the rainbow treasure concept to their own mythological frameworks. Native American traditions developed rainbow bridge stories connecting earthly and spiritual realms. African folklore created rainbow serpent legends linking weather phenomena to ancestral wisdom. Children's literature embraced rainbow treasure hunts as perfect story structures that combine adventure, magic, and educational content about weather phenomena. Hundreds of picture books feature characters chasing rainbow ends while learning about optics, persistence, and accepting disappointment gracefully. The Impossible Quest provides safe frameworks for exploring themes about desire, effort, and realistic expectations. Modern marketing exploits leprechaun rainbow associations to sell everything from breakfast cereals to lottery tickets. Lucky Charms cereal promises magical rainbow experiences in convenient breakfast form. State lotteries use rainbow imagery to suggest that financial rainbows might appear for lucky ticket purchasers. The leprechaun's marketing genius continues generating consumer desire for products connected to rainbow symbolism. Tourism industries capitalize on rainbow treasure hunting through destination marketing that promises visitors might encounter magical rainbow experiences at specific locations. Ireland promotes tourism campaigns featuring rainbow photography opportunities at scenic locations. Hawaii markets rainbow viewing tours that position tourists as modern treasure hunters seeking perfect rainbow encounters rather than leprechaun gold. The psychological appeal of rainbow treasure hunting reflects deeper human needs for hope, wonder, and connection to natural beauty. Chasing rainbows provides socially acceptable excuses for outdoor exploration and weather observation that might otherwise seem purposeless. The Impossible Quest becomes its own reward by encouraging people to notice atmospheric phenomena and appreciate nature's optical artistry. Corporate boardrooms wage invisible rainbow wars using color psychology weapons that most consumers never recognize. Marketing departments deploy specific wavelength combinations designed to trigger purchasing behaviors, emotional responses, and brand loyalty patterns that operate below conscious awareness levels. The innocent rainbow has become capitalism's most sophisticated mind control tool, disguised a cheerful decoration. Fast food chains exploit red and yellow rainbow wavelengths to create psychological urgency and appetite stimulation that drives impulse purchasing decisions. McDonald's iconic red and yellow logo triggers neurological responses that increase heart rate, elevate blood pressure, and stimulate hunger sensations. The color combination creates subconscious associations with speed, excitement, and immediate gratification that encourage quick ordering decisions and rapid restaurant turnover. Blue wavelengths dominate technology company branding because psychological research demonstrates that blue colors increase trust, reliability, and competence perceptions. Facebook, IBM, Intel, and Microsoft all deploy blue-heavy rainbow strategies that subconsciously convince consumers these companies provide stable, trustworthy technological solutions. Blue color choices reduce perceived risk and encourage consumers to share personal information or make expensive technology purchases. Green rainbow wavelengths signal environmental responsibility and health consciousness that commands premium pricing for products positioned as natural or sustainable. Whole Foods. Starbucks and countless organic brands exploit green color psychology to justify higher prices while suggesting their products provide superior health and environmental benefits. Green marketing generates billions in additional revenue by triggering subconscious associations between color and virtue. Luxury brands carefully avoid rainbow color schemes because psychological research shows that multiple bright colors reduce perceived exclusivity and premium value. Channel Rolex and Mercedes-Benz rely on black, white, and metallic color palettes that suggest sophistication, refinement, and exclusivity. Rainbow colors would undermine luxury positioning by creating associations with children's products and mass-market accessibility. Gender-targeted marketing deploys rainbow wavelengths according to culturally conditioned color preferences that begin developing during early childhood. Pink-heavy rainbow strategies target female consumers by exploiting learned associations between pink colors and femininity, nurturing, and emotional sensitivity. Blue-dominant approaches target male consumers through cultural connections between blue wavelengths and strength, reliability, and logical thinking. Seasonal marketing rotates rainbow strategies to match psychological associations between specific wavelengths and time periods throughout the year. Orange and red autumn colors trigger purchasing behaviors during back-to-school and holiday shopping seasons. Pastel rainbow palettes exploit spring renewal psychology to promote cleaning products, fashion, and lifestyle changes. Winter campaigns emphasize blue and white color schemes that suggest freshness, purity, and new beginning opportunities. Digital marketing amplifies rainbow color psychology through screen-based display technologies that provide precise wavelength control impossible with printed materials. Online retailers A and B test different color combinations to optimize conversion rates, click-through behaviors, and shopping cart completion statistics. Email marketing campaigns deploy rainbow color choices based on demographic data and previous purchasing patterns to maximize engagement and sales performance. The rainbow's commercial weaponization extends beyond individual product marketing to entire retail environment design that shapes consumer behavior through comprehensive color psychology manipulation. Shopping malls, grocery stores, and department stores orchestrate rainbow wavelength experiences that guide customer traffic patterns, influence purchasing decisions, and maximize revenue per square foot through scientifically designed color strategies. Astronomers perform the ultimate impossible magic trick every single night. They point telescopes at distant stars. They determine what elements burn inside those nuclear furnaces. They do it across distances that would take light millions or billions of years to cross. This cosmic chemistry analysis relies entirely on rainbow science that transforms starlight into detailed ingredient lists more precise than any earthly laboratory analysis. Every chemical element produces its own unique rainbow fingerprint when heated to stellar temperatures. Hydrogen gas glows with specific wavelengths at 60, 56, 43334, and 410 nanometers that appear as distinct lines across the spectrum. Helium generates completely different wavelength signatures at 588, 51447, and 42 nanometers. Iron creates over 400 distinct spectral lines scattered throughout the rainbow. carbon, oxygen, silicon, and dozens of other elements each broadcast their own unmistakable wavelength signatures. When astronomers split starlight through modern prism systems called spectrographs, they observe thousands of dark absorption lines scattered across the rainbow spectrum. Each dark line represents a specific wavelength that atoms in the star's atmosphere have absorbed before the light reached Earth. By comparing these stellar absorption patterns to laboratory rainbow spectra from known elements, astronomers can identify the exact chemical composition of stars. That works for stars located anywhere in the observable universe. The technique works so precisely that astronomers can measure which elements exist in distant stars. They can also measure their concentrations, temperatures, pressures, and motion patterns. Spectroscopic analysis reveals that distant galaxies contain the same hydrogen, helium, carbon, and oxygen that compose our solar system. The rainbow technique proves that cosmic chemistry operates identically across billions of light-years of space and billions of years of time. Stellar spectroscopy discovered fundamental truths about cosmic evolution that revolutionized our understanding of the universe's chemical development. Early stars contained only hydrogen and helium created during the Big Bang. These first-generation stars forged heavier elements like carbon, oxygen, and iron through nuclear fusion processes. When massive stars exploded as supernovae, they scattered these newly created elements across space, where they became building materials for planets and life. Modern telescopes analyze light from the universe's most distant galaxies. They observe cosmic conditions from when the universe was less than 1 billion years old. The rainbow spectra from these ancient star systems reveal dramatically different chemical compositions. They document how cosmic element production evolved across 13 billion years of stellar activity. Spectroscopy provides time machine capabilities that reveal cosmic history encoded in starlight wavelengths. The James Webb Space Telescope pushes spectroscopic analysis to unprecedented precision levels that detect individual molecules in the atmospheres of planets orbiting other stars. Rainbow analysis of exoplanet atmospheres reveals water vapor, methane, carbon dioxide, and other molecules. Some might indicate geological activity or biological processes on worlds hundreds of light years from Earth. The rainbow technique may eventually identify chemical signatures of extraterrestrial life. It would rely on spectroscopic detection of atmospheric gases that require biological processes to maintain their concentrations. Your smartphone contains rainbow technology worth more than entire cities possessed just 50 years ago. Every digital photo, music track, and video stored on your device relies on optical systems. They manipulate light wavelengths with precision that would astonish Newton. The rainbow physics discovered in 1666 now powers a trillion-dollar technology industry hidden inside devices you carry everywhere. Compact discs demonstrate rainbow physics principles through microscopic engineering that creates artificial rainbow effects for data storage purposes. CD surfaces contain billions of tiny pits arranged in spiral tracks that are exactly 1/4 the wavelength of red laser light. When laser light hits these precisely sized features, it creates constructive and destructive interference patterns that encode digital information. The rainbow-colored reflections you see on CD surfaces result from diffraction effects that spread white light into its component wavelengths. DVD technology advances rainbow engineering by using shorter blue-violet laser wavelengths that can focus on smaller surface features. The shorter wavelengths allow DVD discs to store roughly 7 times more information than CDs in the same physical space. Blu-ray discs push wavelength miniaturization even further using 405 nanometer violet lasers that enable storage densities impossible with longer wavelength systems. Holographic technology represents the ultimate application of rainbow physics to three-dimensional image storage and display. Holograms record not just the intensity of light waves, but also their phase relationships that contain depth information invisible to normal photography. When laser light illuminates a hologram, the recorded interference patterns reconstruct the original light waves. They create three-dimensional images that appear to float in space with perfect parallax and depth cues. Modern fiber optic communication systems transport rainbow wavelengths across continents through glass cables thinner than human hair. Different wavelengths can carry separate information channels simultaneously through the same optical fiber without interfering with each other. A single fiber optic cable can transmit hundreds of different rainbow colors simultaneously. Each carries billions of digital bits per second across thousands of miles with minimal signal loss. Laser technology exploits rainbow physics to create incredibly pure, single-wavelength light sources impossible to achieve through any other means. Surgical lasers use specific wavelengths that particular tissues absorb while leaving neighboring tissues unharmed. Industrial lasers cut materials by focusing rainbow energy into incredibly small spots with power densities that vaporize metal, ceramics, and composites with surgical precision. Liquid crystal displays manipulate rainbow polarization properties to create the color images on your smartphone, computer monitor, and television screen. LCD technology uses electric fields to rotate liquid crystal molecules. They selectively block or transmit different wavelengths through red, green, and blue color filters. Your screen creates millions of colors by combining different intensities of these three rainbow wavelengths. They match the three-cone visual system in human eyes. The global positioning system relies on atomic clocks that measure time using specific microwave frequencies emitted by cesium atoms. GPS accuracy depends on rainbow physics principles that enable time measurements precise to billionths of a second. These atomic rainbow clocks provide the foundation for navigation, financial transactions, power grid synchronization, and telecommunications networks that define modern technological civilization. Scientists have learned to play cosmic architect by arranging matter at the atomic level. They create rainbow colors that don't require any pigments or dyes whatsoever. This nanotechnology revolution builds colors directly from the geometry of light interaction. It uses precisely engineered surface structures smaller than the wavelengths of visible light itself. Nature invented these techniques millions of years ago. Humans are finally beginning to master them. Butterfly wings demonstrate structural color engineering that puts human rainbow technology to shame. Morpho-butterfly wings contain no blue pigments at all. Instead, their wing scales feature microscopic ridges spaced exactly 200 nanometers apart, precisely 1/2 the wavelength of blue light. When light hits these nanostructures, blue wavelengths reflect strongly through constructive interference, while other colors cancel out through destructive interference. The result creates brilliant metallic blue colors that never fade because they depend on physics rather than chemistry. Peacock feathers achieve their iridescent rainbow effects through similar nanostructural engineering that creates colors that shift dramatically with viewing angle. The feather barbules contain microscopic layers of keratin protein separated by precise distances that create thin film interference effects. Different wavelengths constructively interfere at different viewing angles, creating the spectacular color-changing displays that peacocks use for courtship communication. Modern nanotechnology replicates nature's structural color techniques through artificial manufacturing processes that arrange matter with atomic precision. Semiconductor fabrication technology can create surface patterns with features smaller than 10 nanometers, roughly 30 atoms wide. These artificial nanostructures generate rainbow colors through the same interference physics that butterflies and peacocks evolved over millions of years. Structural color technology offers revolutionary advantages over traditional pigment-based color systems. Chemical pigments fade over time as molecular bonds break down under ultraviolet radiation exposure. Structural colors remain permanently brilliant because they depend on physical geometry rather than chemical composition. The nanostructures that create structural colors are essentially indestructible unless the material itself suffers physical damage. Researchers are developing structural color applications for architecture, automotive, paint, and consumer electronics that promise revolutionary advances in color durability and environmental sustainability. Traditional pigments require toxic heavy metals and organic compounds that create environmental hazards during manufacturing and disposal. Structural colors require only abundant elements like silicon, aluminum, and titanium arranged in precise geometric patterns. Self-assembling structural color systems use biological processes to create rainbow nanostructures automatically. Scientists engineer bacteria and other microorganisms to produce protein structures that self-organize into precise patterns that generate specific colors. These biological manufacturing systems could revolutionize color production by eliminating the need for high-temperature processing and toxic chemicals required by current pigment industries. Tunable structural color technology allows real-time color changes through external control signals. Electric fields can alter the spacing between nanostructural layers to shift colors across the entire rainbow spectrum. Applications include camouflage systems that change color to match surroundings. They include architectural surfaces that adjust color for aesthetic or thermal control purposes. They also include display technologies that create images through structural color manipulation rather than traditional LCD or LED approaches. Display technology wages an endless war against human visual perception. Its weapons remain embarrassingly inadequate, despite decades of advancement and billions in research investment. Every screen you've ever viewed displays colors that are crude approximations of real rainbow wavelengths. That includes smartphones, televisions, computer monitors, tablets, and virtual reality headsets. They do not reproduce natural color experiences with full accuracy. The fundamental problem stems from limitations of three-color display systems. They attempt to recreate millions of color experiences using only red, green, and blue light sources. Human eyes contain three cone types that respond to different wavelength ranges, but natural colors result from complex combinations of many wavelengths simultaneously. Display screens mix just three wavelengths to trick your visual system into experiencing colors that don't actually exist in the light reaching your retina. Current LCD and OLED display technologies reproduce only 35 to 40% of the colors human eyes can distinguish. That estimate assumes optimal viewing conditions. The most advanced displays available today fail to reproduce many natural colors. That includes deep ocean blue, forest green, sunset orange, and flower petal colors. They contain spectral combinations impossible to achieve through 3-wavelength mixing. Your screen literally cannot show you accurate colors of most natural objects. The RGB color gamut limitation creates particularly severe problems for professional applications requiring color accuracy. Medical imaging loses critical diagnostic information when tissue colors fall outside display capabilities. Art reproduction fails to capture the authentic color relationships that artists intended. Fashion and cosmetics industries struggle with online sales because screen colors bear little resemblance to actual product appearances under normal lighting conditions. Virtual reality displays face even more severe color reproduction challenges. VR applications require incredibly bright, high-resolution images at close viewing distances. Current VR headsets reproduce barely 25% of human visible colors. They also create chromatic aberration, color banding, and rainbow artifacts. Those artifacts remind users they are viewing artificial displays, not natural environments. Quantum dot display technology represents the current frontier in color reproduction advancement, but still falls far short of perfect color reproduction. Quantum dots can generate much purer red, green, and blue wavelengths than traditional display phosphors. They expand the achievable color gamut to roughly 50% of human vision capabilities. But quantum dot displays still rely on 3-wavelength mixing that cannot reproduce the full complexity of natural rainbow spectra. Laser displays offer theoretical possibilities for much wider color gamuts. They use highly pure single-wavelength light sources, but laser technology creates new problems. These include speckle artifacts, safety concerns from coherent light, and manufacturing costs that remain prohibitively expensive for consumer applications. Laser projection systems currently cost hundreds of thousands of dollars for color performance that still cannot match natural rainbow experiences. The holy grail of perfect color reproduction would require display systems that can generate any combination of wavelengths across the entire visible spectrum. It would essentially create artificial rainbows with complete spectral control. Such technology remains decades away. It may require completely new approaches to light generation. They would need to bypass current limitations of chemical phosphors, quantum dots, and laser systems. Earth's changing climate threatens to alter the atmospheric conditions that create rainbow displays. It could transform one of nature's most beloved phenomena. It could reshape human cultural relationships with weather and optical beauty. The precise balance of atmospheric moisture, temperature gradients, and storm patterns may shift dramatically. Global warming could accelerate that shift across the coming decades. Rising global temperatures alter precipitation patterns in complex ways that directly affect rainbow formation opportunities. Many regions experience fewer but more intense rainfall events. A warming atmosphere holds more moisture, and it can release in concentrated bursts. Those bursts replace the steady shower patterns that are ideal for rainbow generation. The brief. Violent thunderstorms produced by climate change create less stable atmospheric conditions for sustained rainbow displays. Atmospheric humidity changes threaten rainbow visibility through multiple mechanisms that reduce optical clarity and droplet formation efficiency. Increased evaporation rates in warming climates create hazier atmospheric conditions that scatter light before it reaches water droplets suspended in precipitation zones. Higher humidity levels also alter droplet size distributions in ways that reduce color separation efficiency and rainbow brightness. Shifting storm tracks may relocate rainbow viewing opportunities. Altered jet stream patterns can move them away from populated areas. Some regions have enjoyed frequent rainbow sightings for centuries. Traditional rainbow hotspots include Hawaii, Ireland, and the Pacific Northwest. They could experience reduced rainbow frequency. Other regions could gain unexpected rainbow advantages through changing weather patterns. Increased frequency of extreme weather events creates atmospheric conditions too violent for delicate rainbow formation processes. Severe storms generate turbulent air currents that prevent stable water droplet suspension necessary for coherent rainbow displays. Climate change favors dramatic weather phenomena that are spectacular but incompatible with the gentle shower conditions that produce the most beautiful rainbow displays. Air pollution levels may continue increasing in developing regions as economic growth accelerates. It can create atmospheric haze that degrades rainbow visibility, even when meteorological conditions remain favorable. Urban heat island effects in expanding metropolitan areas alter local precipitation patterns. They can reduce rainbow formation opportunities for billions of people living in growing cities worldwide. However, some climate change effects might actually enhance rainbow opportunities in certain locations and seasons. Extended shoulder seasons with more frequent mild precipitation events could increase rainbow viewing windows during spring and fall periods. Arctic regions experiencing increased rainfall due to melting permafrost might gain rainbow opportunities that have been rare throughout human history. Future rainbow science may develop enhanced forecasting capabilities that help people locate optimal rainbow viewing opportunities despite changing climate conditions. Sophisticated atmospheric modeling combined with real-time satellite data could predict rainbow formation probabilities hours or days in advance. It would allow rainbow enthusiasts to position themselves for spectacular displays. Those displays would come from increasingly rare atmospheric alignments. The cultural implications of changing rainbow patterns extend far beyond weather science into fundamental human relationships with natural beauty and wonder. Societies that developed traditions around frequent rainbow appearances may need to adapt their folklore, art, and spiritual practices. These optical phenomena may become less predictable. They may also migrate to different geographical regions entirely. Climate change may force humanity to develop new relationships with rainbow beauty. Those relationships may be based on rarity and unpredictability. They may not rely on the seasonal reliability that shaped thousands of years of rainbow-based cultural traditions.